Welcome to July 3rd's LeetCode challenge. Max sum of rectangle no larger than k. Given an m by n matrix and integer k, return the maximum sum of the rectangle in the matrix such that its sum is no larger than k. It's guaranteed that there will be a rectangle with a sum no larger than k. So given this matrix here, 1, 0, 1, 0, negative 2, 3, you would think that using the, well, I'll explain first. So say if you were to add this rectangle here outlined in blue, it'll give you the sum of 2, which is no larger than k, which is 2. So let's think about this for a bit. So first thing you think of is a brute force approach. Since there's negative numbers, it's probably not a good way of doing this, but if you were to enumerate all the possible rectangles to get the best solution, time complexity would probably be like, m squared n times n squared, so that might not be the most best way of doing it because it's not very clever and takes a very long time. However, you see a little example here using a one-dimensional array here, so you have 2, 2, negative 1, since we're always guaranteed with sum no larger than k. If we were to sum all these together, we get k equals output 3, and our k is 3. So let's kind of work with this kind of idea, working with our one-dimensional array first, and seeing how that works out. So let's see. So we're going to use this idea, let's see, called, let's say we have an array of negative 1, negative 2, and 4. Put a space there. And we want to develop this thing called a, it's called a lookup, where it's going to be an array that's going to store something called a prefix sum, psum. So first we're going to use that to store a prefix sum. So the first thing it's going to have is 0 because there's nothing summing it. And we're going to move through our first index here, which is going to be negative 1. So a prefix sum is going to be a running sum of negative 1 right here. So we're going to have negative 1. So first we're going to have 0 here. So I'm going to put whatever's in the prefix sum into our lookup. And then we're going to sum it again. And then we're going to add that to our lookup. So we're going to have a running sum as we're going along and putting it into our lookup. So then we move to the second array here, which is negative 2. Negative 2 plus negative 1 would be negative 3. We'll just store negative 3 right here in our lookup. And then lastly, we're going to move to 4. So 4 plus negative 3 is going to be 1. And we're going to store 1 into our lookup. So we're going to have this. However, it's we're going to actually rearrange this and put this negative 1 at the end here. But I haven't decided yet. So I'm going to use this idea for one-dimensional array, and how we're going to develop that towards working towards a harder solution. We're using not just one-dimensional, but 2 or 3 or even more dimensions, right? A two-dimensional array. So let's see. For each time we run this algorithm, this updating our prefix sum in a one-dimensional array, we're probably going to do it for each row. And then we're going to do the same thing with the entire the global. So we're going to sum these two together as well, the columns together, and then we're going to do it for each row that way as well. So it's let's see if this approach or kind of background kind of works. Let's get to it. So there's many ways of, this is a hard solution. I mean, yeah, hard question, challenge. So let's first define our dimension. So m by n is going to be the length of the matrix, and then length of the matrix at position 0. So yep. So we're going to first make our rows. So for row in matrix, we are going to start making our array, our matrix. So for I in range, let's see, n-1, what we're gonna do is make our row. So row at index +1 will be incremented to row at I. Alright. So we need to define an output. So our output is, or initialize our output, I should say. Let's it could be none, but that won't work for integer types. So let's call it float of -infinity, just to have some kind of initialization going on. Now we're going to loop through our matrix. So we're going to have a for loop, a nested for loop here. So for I in range of n, for j in range of I to n. So that's for each row you're going through. What do you want to do? So we want to first define our lookup, which is going to be our array of starting at 0. And then we're going to find our prefix sum counter, or prefix sum, or our ongoing sum, I guess, which is going to be initialized to 0. So for each, let's say, each character, each element in our matrix array, let's call it C in range of M. For each, this is individual, each cell in our matrix, on an array, we want to be able to update our prefix sum. So we're going to increment that with the matrix cell at location J. And we want to, if the minus the so if I is greater than 0, so if I is greater than 0, what do we want to do? We want to minus it with the matrix C location at the I minus 1 location, else minus 0. So this is a turning operator here. So that's updating our prefix sum. Now we want to do is update our lookup table, and we're going to do that with bisect left. So let's call this index, or temp variable, I should say. Bisect left. Our lookup and our prefix sum minus k. Because now we have a prefix sum and our lookup already, we're going to build that, and we want to make sure that the prefix sum is within the restraint, within the bounds of k, right? It can't be greater than k because that's the condition. And we want so first we define our index. Yeah. So if our index is greater or equal to 0, and our index is less than the length of our lookup table, what we want to do is update our output to be the max of the output and our prefix sum minus the lookup at the location index. Then we want to insort, so bisect insort. So we want to sort using a sorted type of approach to the insort. We want to insort lookup and the prefix sum. because we want to put the the last sum at the end of the lookup, and then return our output. Alright, let's see if this is even close to working. Oh, let's see, output. Finished. Oh, that doesn't look good. Let's see, first we define our m and n side lengths. Okay, for each row in the matrix, we're going to make the columns for it. Alright, and the output is going to be a float of a negative infinite number. So for I in range n nested with for j in range I to n, we're going to make a lookup table and a prefix sum counter. So for each cell in our matrix, we're going to increment our prefix sum with the matrix at location C, cell j, minus our if the index, if I is greater than 0, we're going to have minus the cell at matrix C in the I minus 1 location, else we're going to minus 0. And then we define an index number here, which is bisect left, where we have the lookup and the prefix sum minus k, because we want to not be within our outside our bounds. So if the index is greater than or equal to 0, and the index is less than the length of lookup, we want to update our output with max of the output and the prefix sum minus lookup at the index. And then we want to sort that using bisect insort with lookup and the prefix sum, and we want to return the output as well. Alright, that seems to be should work. Please work. Alright, accepted. So this approach is using using a prefix sum on a one-dimensional array, and then we eventually sorted it using bisect sort. It's not really using a sort container, it's just more like using the bisect function to sort it. But in terms of time complexity, I believe that it is. Let's go through this. So we have a nested for loop here going through. So we have, this is the row, which is n. So n, big O of n, times m squared times no wait, this is m, this is let's see, big O of m squared times n times the log of n, because for we iterate, it's a lot. I'm not entirely sure about that, but the space complexity is a big O of n because we store it in our as a number. So we do have a lookup, but we never have to return it. So yeah, that would probably be our. I could be totally wrong in terms of space complexity and time complexity, but that's a hard question. So that's pretty much all I got. Have a good one.